So it's my great pleasure to introduce Fausto Milletarì, who is currently a lead of applied AI at Johnson & Johnson. And he is currently focusing on problems related to surgical data science, surgical robotics, and video analytics. During his PhD, he has published several works in the field of computer vision applied to medicine, and in particular to radiology and ultrasound imaging. His research has also impacted his work at Butterfly Networking Corporation and NVIDIA Corporation, where he has had the opportunity of transferring some of his research into products. It is actually one thing to write a research paper and turning that into a product, and that's a huge endeavor. And today, he's going to be telling us about volumetric medical image processing with deep learning. So Fausto, the floor is yours.
Thank you very much. Thank you very much. So I would like to thank everybody who is joining. I think the room is pretty full, so thank you. What I want to present today is some of the research I've been doing and some of the findings we have been able to uncover a little bit during my PhD and a little bit during the time at NVIDIA. There is not much J&J material. It's a little bit of still in the making, still secretive. So I prefer to focus on things that that will, it's more common knowledge domain. And also I've been asked to present around VNET, which is the more impactful work I've done. I was lucky just once. I just got one impactful work. The rest is all okay. So I will present that one and maybe some insight about other beliefs that I hold about how you integrate humans in the loop, which in my opinion is a very important thing, especially when you talk about products. So, I mean, this slide you probably have seen in many NVIDIA presentation. In fact, I've kind of borrowed from there. Shows the impact of deep learning and the momentum that we have seen in the last years. You know better than I that there is nothing mystical about deep learning, but it turns out it works particularly well because we are at this intersection between computational power increasing and data being available and being, stored consistently, pretty much as a trace of everything we do or everything we go through. And so these data sets are available, there's more compute, and these are quite old statistics now, 2017, 2015. You can imagine that the exponential growth has been going on unchanged. So right now, these numbers are pretty big. I'm sorry, I don't have new ones, but yeah. So beyond research, we have seen a lot of news, AI-powered devices that can do diagnosis, they receive FDA blessing. Zebra Medical has done a lot of things. Google AI to use retinal images reveal cardiovascular risk factor. Many of these have been toy problems or toy solution, I would say, but others are much more present. And one thing I've been seeing, which is not in these actually in this slide, is two companies I've been working with. One was Butterfly Network, which has created an AI-powered portable ultrasound device you attach to the phone, and it runs, and it can do awesome things. And Hyperfine, which uses deep learning to do MRI reconstruction from a milli-Tesla magnetic field signal. So you don't need a magnet almost. There is a very weak magnet in the machine, but then AI can fill in the blanks and actually give an accurate and really not only realistic, but accurate image of the body or the brain, especially. They are focusing on the brain. Basically, it's a portable MRI machine, which is pretty crazy if you think about it. And it's very challenging. A lot of models in deep learning, there's been some sort of a Cambrian explosion. This is a slide that also you'll find on NVIDIA slide decks. The CEO always likes to present this one. where we have convolutional network and different variation on this theme, starting from AlexNet, going to things like batch norm and fully convolutional network with encoder and decoder parts, dropout, and so on. Recurrent networks. Right now, we are seeing a lot of attention and models, attention-based model there. GAN, generative adversarial networks, where we try to synthesize something that makes sense to the human eye qualitatively, or to better yet, a discriminator. So kind of reaching an equilibrium between generating something realistic and being able to tell what is real and what's fake. Reinforcement learning, it's also very interesting, and we are going now beyond games, beyond playing Atari, and new species of deep learning models that we will see up and coming soon. For what concerns fully convolutional network, this is something I've been doing personally in the scope of radiology, where I have been one of the first, or the people we have been, because there are also other people involved. We have been, let's say, using very early on convolutional network for 3D images, so for volumes. And this because most of the medical data out there is really volumetric. Like the human body is a volume, and beyond, actually, you have things that you can measure that give raise to more dimension than 3. You can think about tractography. You can think about this other last one. This is an ultrasound view of the left ventricle of the heart. This is the rightmost picture, which is analyzed over time. And same with the prostate. We could even have multi-channel images with different MRI modalities, and the same for the brain tumor segmentation. And one of the work that I have been lucky enough to be able to publish in time to get some recognition is VNET. It has had 3,188 citation since it was published. I think it's 4 years, maybe 5 now, approaching 5. And it has been the most cited paper in a lot of contexts, if you want to, measure in that way. But it's really a very simple idea. It's inspired to the VNET work, and what it does is turning it at 3D and adding a couple of variation that have been important. Prior to VNET, people thought that the dice loss, so the dice overlap coefficient, could not be used to learn because it was not differentiable, and they had a struggle to create a differentiable dice loss. This was the time before autodiff, so you needed to create your backward pass by yourself and compute gradients by yourself. Apparently, it was hard enough to compute those gradients. It's not hard at all, but there were some. That's the reason why we were able to innovate there. We are using in VNET 3D convolutions with 3D receptive field, something very well understood now, especially now that we have temporal convolution, where people are using actually 3D convolution on a day-to-day basis to predict stuff on videos. We had to implement the 3D layers, but this is stuff of the past right now. Now it's all understood. And we have done a couple of other innovation, but one of the things that has enabled us really to do this work is the GPU with more memory. So we had this 12 gigabyte GPU that seemed a lot at the time, and we were able to fit the whole network there without having to resort to crazy swapping or caching mechanism. And so we could create a 3D receptive field. We could see very far into the volume, and we could see the whole volume. So X, Y, and Z direction all together. And we have then derived this dice loss, and we have done it in this way. And you can see that this dice loss term has one, so it's written with the exponents. So the denominator as pi, which is the, dice is defined as 2 times the overlap over the union of 2 volumes. So if you have 2 binary volumes, you can just compute the overlap of these 2 and then multiply by 2 and then divide by the union of the total number of pixels that these 2 volumes have, which is 1. So it's binary volumes. But then we need to square these 2 the predicted pixel and the ground truth pixel, even if they're just one. And this is in order to make the gradient stabilize at 0 when we approach the maximum of the dice. Otherwise, this term will not actually yield a 0 gradient. And so that's why we are formulating this way. A lot of people get that wrong and still write it in this way. As long as you are considering the value, these two are equal. But when you consider the gradients, they're profoundly different. If you derive it yourself, probably you can do it in half a second. You're going to see it. But this one goes to 0 and this one doesn't. This one was the first thing we pointed out in the paper. Concatenation, then we have, of course, added a few other things like concatenation of long skip connection is done with sums instead of pure concatenation of features like VNET does. And the reason is that we save memory, basically. Batch norm, at the beginning, we didn't use it, but then as soon as group norm came out, we tried out and it was really good. The reason why you cannot use batch norm is that you don't really have big batches. The network requires a lot of memory, so you don't have these big batches. And the dice loss, of course, can be also extended to multi-class dice. There are millions of formulations for that. People have tried multiple things, not millions, but there are a few formulations. And there are variations of VNET architecture that perform better. So what can we say about VNET? It's outdated. VNET is outdated. You should not be using it. But it contains some lessons and some other, and its simplicity nowadays, because of how PyTorch works and how things work, might help you to trace a baseline or might help you to get, going in the field of 3D segmentation or even, segmentation mostly. We tried on a few datasets. The PROMIS 2012 MRI dataset, limited training data. We augmented, we did all the kind of things. This is described in the paper. And we actually didn't get better than the previous method, which was not based on deep learning, but was from a company. And this is mostly because we didn't really implement everything right, I believe. And also because these guys have really spent time to build something that was product grade. But still, we classified so we arrived at a good position in this challenge. And it was a pretty fast runtime of 1 second. This is a snap of fingers on an old GPU. This was a K40. Was going, imagine on a V100 is really milliseconds. So it's pretty cool. We started doing also multi-class CT segmentation at that point with something that we termed HD VNET or VNET 2.0. We have increased the resolution. We have done a few changes. These are a study we have done with Japan, and the results also look better, more smooth, a bit better in general. We had done this left ventricle segmentation, which was also presented at one NVIDIA keynote when we started at NVIDIA doing some sort of healthcare-related imaging. That was raising a little bit of hype. But there we really got good results. And this was just because we didn't do anything. We just doubled the resolution everywhere, used huge GPUs, and that was it. So nothing to be very proud of, but there was still something to squeeze from VNET, some juice to take. And it had 8 times more voxels, so it started becoming complex. At the time, I was taking care of a package called tomat.cloud, which was some sort of remote inference. It was available through that one, but I left this note here by mistake, obviously. I mean, Tomat still run, or you can still use it to do inference and try out your methods on top of a visualization tool of like Slicer or others, but it's not anymore just available right out of the box, just for you to know. And we start seeing that the image resolution will start improving the performance, and we start getting performances that were higher and higher given the number of voxels. And we achieved the maximum resolution at DGX2, where we could really use 16 GPUs to do that. Kind of a waste, if you ask me. But, just was a nice point to NVIDIA at the time. But then we came to the conclusion and we start saying, why are we taking away the job of radiologists? Like, seriously, in the sense, there are a lot of people saying, oh, AI is not trying to take away the job of the radiologist, or it's impossible to replace a radiologist. But de facto, we are taking methods that are not that great, honestly, and we are trying to make them do something that somebody else has spent a year to train. And although it's true that some people have also trained pigeon to do the job of the radiologist, and it kind of worked, surprisingly, not to demean the radiologist, just a kind of amazing, weird thing that you can look up on the internet, about the collection of weird stuff. But still, these guys have trained and they are very skilled. So why are we just relying on previously acquired information? Because what are you doing really when you train a neural network? You are taking some examples and some answers, which represent a crystallization. It's the knowledge of some people crystallized in a bunch of videos or volumes plus annotation. And the annotation is what crystallizes their knowledge. And then you tell to these people, okay, I got it. I don't want to have your knowledge anymore. But why? The people are still involved. They need to be still involved. Why don't we just make their work a little bit easier by making things interactive? And it turns out that interactive CNNs are not so easy because people are really focusing on automating. There is not so much literature on how to do things in an interactive way, or at least there was not in 2016 when we looked at this. 17 probably. Yeah, no, maybe it was later. It was May 2019. Yeah, 2019 when we did this. Yeah. So when you want to take expert knowledge at runtime, so not in the training set, you can use expert knowledge at runtime. You can either resort to a manual approach. There is no model, there is nothing. People just go there pixel by pixel. Tedious work, a lot of variability, not good. Or you can just take an interactive method that does not use any pre-trained training example that is not trained on anything. Or you can even use an interactive method that is actually training on something, using some sort of previous crystallized knowledge on top of a training set. Or you can make a automatic deep learning method where you just use that knowledge and you don't use the person anymore. The person knowledge anymore. So this automatic DL model, as I explained profusely, is not what we are looking for. We are looking at interactive methods. And there are shallow interactive methods, let's say, the deep interactive methods. So techniques such as graph cuts, you know better than I do what they are. Like you try to find some sort of, so you organize all the voxels in a volume in a graph, and you try to find some sort of optimization of how you can divide this graph into subgraphs. You have random walks, which is even cooler because it turns out that whatever, so the result of those mathematical optimization problem, or the solution of a random walk is actually corresponding to simulating with a very large number of random walker how they would propagate in a network of streets, let's say in a network of paths. That are as wider as the similarity between two voxels. So in other words, you group again together two things that are similar, together, and things that are not similar, you're cutting them loose, cutting them apart. So random walk is a slightly cooler version of a graph cut algorithm, and they work via scribbles. So you scribble and you get it. They require a pretty high amount of interactions. Not too much runtime because you can get the solution pretty quickly, but the interactions is like these algorithms tend to get wrong a lot of things, and so you need to correct them and put more and more scribbles, and then implementing in commercial software. Really, they are used, so they're already good enough. The deep interactive methods, like the one we are looking at in this work, they use bounding boxes, clicks, and scribbles, and even other interaction methods. And they're applied to tasks mainly such as mass annotation. More than production, they're used more for annotation. And they require just a few interactions compared to the shallow methods, which are intuitive. Many of them cannot support an unlimited number of interactions, or they break if you interact too much. And other of them are really just tailored to the annotation, not to a usage. So what we have done is then we have basically created a method that is more suited for being used online. It can be used for annotation, of course. You can use it as much as you want, but it's also for online use. And this medical, so the relevance in radiology is that medical tasks are anyway done offline, so you can take time to do them. If you take 1 second to do a prediction on a volume, and then you don't give the radiologist any possibility to change their results, you're actually doing much more damage than requiring 5 minutes of their time, because they actually will lose also trust on the system, since 9 times out of 10 that you ask something, the system runs in 1 second and produces something wrong. But what you truly want is a system that is helping you and is supporting you. So, we can also do a lot of continuous learning. We can generate new training data, because now we have a human in the loop. So this human is supposed to correct the mistakes, especially in medical field, this is true. And so you can actually get for free some newly annotated data you can use, because it's unlikely that the radiologist who has an interactive method at their disposal is looking at a mistake, a segmentation mistake, and does not do anything about it, and just leaves it there. It's very unlikely. So what happens is that they're going to correct it, and then you can say, okay, this scan was seen by radiologists and they corrected it. I'm pretty confident it's good. I can use for learning, for training again. And our proposal is to use a very standard network architecture and a very simple interaction method that is based on clicks, simple clicks on an image. And the resulting algorithm reduces time and improves the results of segmentation. So it's better than any automatic methods, and it's reducing time compared to manual segmentation, and sometimes even compared to automatic methods. So we take a unit, we use batch norm, because now we have batches. So this is 2D, even if the title of the presentation is about 3D. We have tried in 3D. The problem is always the resolution. But we can use this 2D method on a stack of images, which becomes a 3D image, which is not optimal, but it can be improved upon. And we use Adam and dice loss to train. And we ask to the user, use the left button of the mouse to attract foreground. So wherever you think there should be foreground, wherever you think the anatomy of the interest is, click with the left button, and wherever you think there should be background, you click with the right button of the mouse. And how we formulate this in practice for the network to ingest is that we are taking the CT image as a grayscale, or even as a multi-channel image, but let's say grayscale image, CT, goes in, and then we supply 2 different channels, one that contains representation of the foreground clicks, and the other that contains a representation of the background clicks. And what does it mean, a representation of the left and the foreground and background clicks? It means that we are actually so we are placing a little Gaussian kind of intensity pattern, so some sort of blob in correspondence of every location the user has clicked. So in the end, if the user has clicked 3 times with the left button signifying foreground and 2 times with the right button signifying background, the first channel for foreground will have 3 little Gaussians placed in correspondence of this click, and the background channel will have 2 little Gaussian corresponding to the other background clicks imposed on top. So we take the signal, we put inside the network, and we say, okay, now you've got to predict where you think foreground is and where you think background is. And of course, now there is the problem. How do you train something like that? I mean, the same image needs to go through the network multiple times. And then depending on the click, you want a completely different answer. Is that going to work at all? It turns out, yes. What you do is you take a CT image with multiple classes, and you split this training example. Is the same intensities, but every time you want a different anatomy, you associate this very same intensity with a different region. So at the beginning, the network is extremely confused, because it's like, I have this picture, which is a lot of pixels, and then this couple of Gaussians here in the back in the other 2 channels that don't look like anything to me. And now you're telling me that this is a liver, but it's also a pancreas, but it's also a kidney. Like that does not work, right? Like you cannot really do that. So initially the network is completely lost, but after a few iterations, it starts associating where the foreground occurs compared to where the foreground clicks are, and where the background occurs and the background click are. And how do you achieve this? You need to have the network play with itself. It's some sort of almost like you would do in reinforcement learning, that you have some sort of environment you can play with. Here it's much more simple, of course, and it's because you have supervision signal, you know about it, but you basically need to have a mechanism that say, given a click and given this image, dear network, what are you giving me back? Oh, this is the foreground. Then it's like, okay, I place you a correction click based on what you have predicted, based on the mistake you have made. I place a background or foreground click in an automated manner, artificially, using a heuristic, and I supply the same image again. And I say, now what do you see there? And you basically keep doing this over and over and over again until you train and you start getting the good results you're expecting. And you do this with a variable amount of clicks. Sometimes you just ask the network to give you a prediction given a first click, then a second click, and then a third click. And then you learn from the very last one. So you don't propagate gradients for the first two interactions, you just propagate gradients for the last one. And sometimes you just ask the network to predict right at the first click. Sometimes you superimpose 15 clicks going to address very small mistakes. And how does the click placing work? You impose this sort of heuristic where you say, people are going to address biggest mistake first. So having a disparity map where you miss parts of the foreground, go to the part where you miss the most and place a click more or less in the middle of it with a certain probability, clearly. Not really in the middle of it, on a pixel that belongs to that wrong region. So place this correction click on the wrong region according to a certain probability, which is higher in the middle of the region and lower at the border. Why? Because people tend to address biggest mistake first and then become perfectionists later, maybe. And second thing is people try to click always more or less at the center of regions. When you see a mistake, you're not gonna click at the very last pixel of this mistake, you're gonna click right in the middle, especially when it's big, right? So that's how it works. So you have this simulator of human interaction, very important piece, very important piece. So this tells you you can play with neural networks and make them do crazy things. You can confuse them, but then ask them to pick up on a very small signal, a very insignificant thing, which they will start treasure and they will start use to yield you the result you're expecting. And so what causes realistic interaction and so on. I mean, here there's a little bit more explanation on how we get these error maps and the click probabilities. So we just take the ground truth, we say this minus the prediction, and then we see where was the biggest area that was missed. So where there should have been foreground and there is background instead. What's the biggest area where we predicted too much? And in this case, where there is a foreground region, but there should have been background instead. And then choose between which one to address first with a certain probability, and then place a click with a certain probability. That's how it works. But I mean, I'll send you the slides so you can look at it. Many people don't get it immediately. It's a little bit convoluted, just to remain in the same train of thought, convoluted. Okay, the network turns out is learning foregroundness, is learning human click here. This region must have some property that make it special. So at the beginning, it's funny. You see in the first 20 epochs or so, after the initial confusion, you place a click, you're going to get a slightly bigger Gaussian than the one you represented the click with, because the network does not really know what you want. And then later, you place an identical click, in one case on a very small kidney, and the second case on a very big liver, is going to give you the whole liver and the whole kidney. So the same click is the same representation, it does not change. Due to its position, due to the texture of that image, due to factors similar to these, you can just click, and with exactly the same type of interaction, producing the same type of guidance signal, you get two completely different results, depending on where you are in the image, which is pretty cool. The method is also well behaved because the more you click, the better you get. Even if you put 100 clicks, it's not gonna go crazy. And this is probably because we are using this Gaussian kind of representation where you have, if you put a lot of Gaussians together, in the end, you're gonna get a lot of, higher, some sort of mixture where you cannot create so much damage. You also normalize this kind of guidance map, okay? So when you superimpose multiple Gaussians, you try to get them normalized. So then they can reach so it's just kind of normalized. Can you segment stuff you have never been before? Yes, you can segment stuff that is coherent, and this proves that the network is learning foregroundness. It's really funny because people struggle getting an automatic method work for the anatomy in the abdomen, but then if there is a tumor, the automatic method will just miss it completely. While with this method, you can just say, wait a moment, let me click on the tumor a couple of times, and then you highlight it. And now you can compute its volume or whatever you want. So here you can see a few interactions. This first part is the known region, the first 4 columns. These are 4 different clicks. From top to bottom is 4 different clicks. You click once and it gets basically most of the liver, second time, third time, fourth time, you're fine. A couple of clicks on the kidney and you're fine. On the spleen, couple of clicks, fine. And then you have the unknown regions over there that you never seen during training at all. It's like this muscle near the spine. You just click once, twice, 3 times, pretty much perfect. And then you have there a very tiny vessel, very tiny object. The Gaussian is going to be bigger than this object for sure, the click Gaussian. And bam, you get it. A little bit more clicks maybe, but you get it. So that's the important part. So we tried it on previously seen classes on the test set, of course, not the training set, but classes that we have trained for, liver, spleen, whatever, and previously unseen data sets. So same classes, but on a data set that was completely disjoint, taken from a different center, whatever, different data source. And then a completely unseen classes, so new anatomy, brand new, that we never trained for. We just didn't have in the training set. And by the second click, we get better results compared to most automatic methods. Right at the first click for colon cancer, we get a better result, the state of the art. At the time this was written. We get the best results in general for DICE, Hausdorff distance, and mean average distance. By making basically for a certain number of clicks, an acceptable number of clicks, the method is just better compared to anything, compared to different methods that have won the challenge. So the BCV is the, okay, now I don't remember this, but there is a reference for sure. And then there is also, I use this BCV, nobody tells me what it is here. I'm just missing the word right now. It was a segmentation beyond the crane vault because it was abdominal segmentation. And then there was this other segmentation challenge called the medical segmentation decathlon. We also excelled there. So it was pretty cool. And here there is a demo. Let's see if it runs. I mean, it's video, of course. This was web-based visualization tool I'd made at the time. It takes just a little bit of time to load. And now I go on segmenting. So slice by slice, unfortunately. So this is the kidney, and then I can carry the segmentation to the next slice and correct. Pam, 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 and then you see. So, and then I can make correction as I like. So even there were a couple that were not necessary. Then there is a vessel in the middle of the picture, at the top actually, which I would like to highlight, never seen during training. That the thing is nothing, I don't even know what that is. I just click, of course it takes more clicks, but in the end, the system will get it. It's pretty funny also to use, you know. Then how do we build useful AI? Because not all the deep learning methods are created equal. Most of current research is done on toy problems. We want to go to products maybe. And the toy problems are useful because it gives you this very controlled environment you run things on, and you should never go away from that, not even when you are in industry. I think you should have this very good gym, like some sort of gym environment where you can just try things out and assess baselines and run benchmarks on toy problems. But you need to consider some real life things too, especially when we get ambitious. The AI won't replace radiologists, but radiologists that use AI will replace radiologists who don't. And this is something that smart people keep saying. And then we need to treasure this user base that we have in radiology, especially. We have trained professionals who are willing to use AI, who are really, or AI, abusing the term. We are having a discussion on LinkedIn that you should not be calling everything AI. I think we can abuse the term. We understand each other, but these guys want to train, want to use these algorithms. They want to have computers helping their job, but they don't want to be replaced. They want to be at the forefront of their field, exactly as we want. And so I think that we need to go in the direction of producing interactive methods, especially for all those situations where we can afford the interaction in terms of runtime, in terms of human expertise being present. Of course, if you are asking to perform radiologist task to the man of the street, okay, you might want an automatic method. But if you have a whatsoever trained radiologist that is decent, you should maybe use part of the knowledge. Maybe something looks very weird, alert the radiologist, but don't try to make their job. And we should keep expert in the loop. The accuracy is important for what concerns ML and deep learning for radiology. We need to implement strategies to reduce error, and some strategies have actually worked even with automatic methods. For example, you can have a voting strategy where whenever you want to assess a contour, you have actually half voting or some sort of voting strategy to get it to as a majority, as the result of a majority opinion from multiple parts of the anatomy. You can use statistical models, PCA and stuff like that to model shapes and do statistical shape modeling, even with deep learning and better network architecture. That's always a possibility, but interactivity beats them all. Keep expert in the loop, I already say about it. And then a lot of architecture standard. I will not look into reinventing the wheel. In fact, I think that Andrew Ng today was saying something around AI or deep learning, whatever, needs to be more data-centric. It's all about data preparation. It's all about being systematic. It's all about tracking results. And there are really a lot of new tools that are out there you can use to track your result, to be sure that your thoughts that seem so good are also translating in a real improvement of the results. Because now you can track, you can benchmark, you can use the data you have with consistency. And so, the other techniques, of course, one needs to stay up to date, but in general, data is more important than architecture as of today. Fortunately or unfortunately, it is. So this was it from my side. I hope I didn't take too much time, and I hope I was not speaking too fast and with not too much of an Italian accent. So hopefully it was intelligible.